Good day, class. For this set of slides, we will be talking about multiple reactor systems. So, they can be made of the same kind of reactor or a combination of the different reactors that we have discussed already. But what we will be having for these systems are all flow reactors. This would be our second to the last topic. So, the last topic would be recycle reactor, and that would be it for this semester for chemical reaction engineering. So the last two topics were already assigned to you for reporting in the form of video presentations. So let's go through these multiple reactor systems, starting with the plug flow reactor in series. So if we have a series of plug flow reactors, this is how we represent the molar feed rates and the conversion of each of the streams that come in and out of a particular reactor. So we have the molar feed rate here entering the first PFR in the series, FA1 for the molar feed rate for the second PFR in the series, and FA2 for the molar feed rate for the third PFR in series. So the molar feed rate that is entering a succeeding PFR, of course, came from the previous PFR. So we label the conversion as XAO if it is for the conversion of the stream that enters the first PFR in series, then XA1 for the second conversion, referring to the degree of conversion in the first PFR. Then XA2 or X2 for the conversion in the second, and XA3 for the conversion in the third. So for these PFRs in series, the ratio of the initial concentration to the final concentration here that leaves your last uh, PFR in the series would be equal to this particular formula or expression. So that would be 1 plus the product of the initial concentration or the concentration of the stream that entered the first PFR, the rate constant, and the tau p, which is the residence time. This one is the total residence time of your processed feed in all three reactors. So this is already the total residence time, okay, the tau p for our PFR in series. Now, if PFRs in series or if PFRs are arranged in series or parallels, these parallel connections, these are the two formulas that you will see also available written in GenCo, please. The first one is for the volume. So it allows you to calculate for the volume of the ith reactor in an N PFRs connected in series. So this is for series connection. So the volume of the ith reactor divided by the molar feed rate to the first PFR in the series is equal to the integral of the differential of the conversion divided by the rate law. Now, your limits of integration here will be the initial conversion of the stream that is being processed by this ith reactor. So that is why you have X sub I1. So if you are determining the volume of the third reactor, this would be the conversion from the second reactor because this one is I minus 1. And this one is, of course, the conversion in the particular reactor in which we are computing for the volume of. So for NPFRs in series, so whether they are of the same size or not, the volume can be summed up, which is equivalent to the individual volumes of the PFRs. And X sub n is the conversion in reactor N. How do we, by the way, differentiate conversion for the entire system of reactors already or conversion for a particular reactor? So if the X does not have any number here, subscript, then it's referring to the conversion already of your processed feed, referring to the overall conversion of your process feed in your series of reactors. So this may be for a PFR in series or for an MFR in series. But if a particular conversion just like this has a subscript n, then it's referring to the conversion in that particular reactor, whatever flow reactor that be. So for the nth reactor, in a PFR series of reactors, this will be how you uh, represent the performance equation. So the total volume, which is now the sum of all the volumes of your PFRs in series divided by the molar feed rate, is equal to the integral from 0 to xn. Take note where xn is the conversion in the nth reactor. And this one is 0 because this is assumed that your feed is not initially converted or was not initially converted when it entered the first PFR. But if it's already converted, then this should not be equal to 0. This is just for the case wherein conversion or your feed that is being processed is partially converted already. Again, take note of this formula for the performance equation of an NPFRs in series where the V is the sum of the volume of the individual PFRs and X sub N is the conversion on the nth reactor. Okay, this one in form is comparable to this form that you have in here, all being used for PFRs in series. So this one, your feed to the first PFR is initially converted. This one is not initially converted, meaning there's no conversion for the particular species that we are following through or monitoring the conversion of in the system. Now, NPFRs in series with a total volume V gives the same conversion as a single PFR of volume V. So whether you have similar sizes or PFRs that are not the same in sizes, if you take the total volume of that would be equivalent to one PFR of the same total volume. So the conversion for for the system and just one PFR of equal volume to the system would just be the same. For PFRs connected in parallel or in parallel series combination, so a single reactor can be used of volume equal to the total volume of the combination. And take note of this, as long as the composition of the streams that met are the same. So if you have a parallel connection, it is important that the composition of the streams that will be summed up or that will meet will be the same. So the composition of the streams that meet should be the same. And we will not have any problem with that. Another thing, this one tells you that the composition of the streams that meet are the same in the case of parallel connections. Another thing that we should add there is that the ratio of the volume to the F or the residence time must be the same also for each parallel line. So aside from the composition of the streams that met being equal, if you have a parallel connection for PFRs, the residence time in each of the connection that is parallel to one another should be the same, must be the same. So the tau or the ratio of the V to the molar feed rate. It is expected that the concentration of the reactant decreases progressively through your series of PFRs. Now, let's go to the case in which we have equal sized MFRs in series. So the manner of representing conversions, concentration of the stream, smaller feed rates is exactly the same to that of the PFR. So you use a subscript O if it's referring to the composition, conversion, molar feed rate to the first of your MFR in the series. Then the concentration conversion of the stream that leaves a particular unit will have the subscript equal to the number of that particular unit. So if it's coming from PFR number 2 or PFRI, the labeling of the concentration and conversion, same thing with the molar feed rate, would be same as that of the first. Subscript is equal to the number of the reactor in which that particular concentration or conversion is referring to. Okay, so this is how we place in conversion, concentration. This one is volumetric flow rate. Now, if you notice, this V here and this V here are the same. So for our equal size MFRs in series, even if they are not of equal size, the volumetric flow rate has to be the same. Otherwise, one reactor may overflow or one reactor may go dry if the volumetric flow rates are not equal. So volumetric flow rates have to be equal. So that's the only thing in this series that will be equal. Residence time, of course, will be equal if we have equal sized MFRs. But if it's not equal sized MFRs, then the space time will not be the same. Now, this formula that I placed here came from Levenspiel rather. This is for equal sized MFRs in series with order equal to 1, and you have this expansion factor equal to 0. So meaning your system here, your process is a constant density process, or the system is a constant density system. So how we account for the space-time is actually the same as our formula when we were studying single ideal reactors. So concentration multiplied to the volume of the reactor divided by the molar feed rate. Or simply put, that would be the volume of that particular reactor divided by the volumetric flow rate. In terms of concentrations and conversion, the numerator will represent the part that has been converted divided by the rate law. Okay, this is the part that has been converted. This one is also referring to the part that has been converted, or the concentration that was converted to the product. Another formula that we can use is the ratio of concentration. Let's say, for example, C sub 2 over C sub 3. If this I is 3, then this must be C sub 2. And that should be equal to 1 plus K tau I. Tau I is the residence time for each of the units, because now it's specific as I, so it's referring to the residence time in a particular unit. And since they are equal size, so this residence time or time constant is just the same. Now, another formula that you will find very useful in processing problems concerning MFRs in series in relation also to a PFR is this: the ratio of the initial concentration or of the feed that enters the first reactor to the concentration of the effluent from the last reactor being equal to 1 over 1 minus the conversion in the last reactor. So N here is the last reactor. This is also equated to the expression 1 plus K tau I. Okay, residence time again, or space time for a particular reactor, since it's all equal for this equal sized MFRs, raised to the number of reactors in the series or in your system. The space-time for these N reactors would be, of course, common sense would tell us, will be the number of reactors times the space-time in each of the reactors. So tau I, as I have mentioned, is the space-time for one particular reactor. So if you multiply it to the number of reactors in your system, that would be the total space-time for your N reactors. And this is also another formula that will account for the total residence time in your N reactors for equal sized MFRs in series. Now, if this particular equal sized MFRs is increased in number, the behavior of such MFRs in series when they are already very large, or you have an infinite number of equal MFRs in series, its behavior is comparable to that of the plug flow reactor. So when n approaches infinity, meaning the value is very large, its behavior is comparable to a plug flow reactor whose residence time is given by this formula, dependent on the rate constant, the initial concentration, and the final concentration leaving that particular plug flow reactor. But this only happens when we make the number of these equal sized MFRs in series large. Now, for n MFRs in series, the larger the number of n, the closer the behavior of the series to that of a PFR with volume equal to the sum of the volumes of the MFRs in series. So it was already mentioned here. Okay? So if we increase the number of MFRs, its behavior will be comparable to that of a single PFR, whose volume, of course, has to be equal to the sum of the volumes of the MFRs in series. A PFR, however, is more efficient than an MFR for reactions whose rates increase with reactant concentration, such as an nth order irreversible reaction. Now, we have learned in our topic in size comparisons of uh, reactors when we compare conversion and size for a particular reactor. We have actually learned, yeah, I hope you were able to grasp that your PFR is more efficient than an MFR, as long as we're talking of nth order reactions which are greater than 1. And they are also irreversible reactions. So nth order reactions or nth order irreversible reactions. Now, space-time is the same for equal size MFR. So I have mentioned that already. And in MFR in series, concentration drops immediately to a low value. Unlike in the PFR, it's a gradual decrease in the value of the concentration. But in the case of an MFR, there's a drastic decrease in the concentration of the material that is being processed inside your reactors. With mixed flow reactors, it is more convenient to develop the necessary equations in terms of concentration rather than fractional conversion. And since we know that for an MFR, our performance equation is not an integral expression, then it is suggested that you will write equations in terms of concentrations rather than fractional conversion. So you can, if I may suggest, you can change the CaOXA in the numerator of the performance equation for an MFR into its equivalent in concentration. So if CaOXA is the part that has been converted, then that would be the initial concentration minus the final concentration, because your initial concentration minus the final concentration will also represent the part that has been converted equivalent to, let's say, for example, CaOXA. So this is just but a suggestion, but it really depends on the given in the problem. Now, whereas in your PFR, you can have the leeway of representing your performance equation in terms of XA or CA. Now, the optimum size ratio for two mixed reactors in series is found to be dependent on kinetics and on the degree of conversion. So the the optimum ratio of, let's say, two mixed reactors in series, whether one will be very large compared to the other, or one will be just, let's say, for example, 40% of the size of the other, or 30% of the size of the other. This is dependent on two factors: the kinetics of reaction and the degree of conversion sought. So when order is equal to 1, equal size reactors is the best choice. So meaning there's no need for us to compute or determine the optimum size ratio. So when we speak of the optimum size ratio, like for example, V2 over V1, the V2 and the V1 that I am referring to is the volume of the second reactor compared to the volume of the first reactor. So that is why it's ratio. So it's an optimum size ratio. So there's no need for us to determine this when we talk about first order reactions. So N is equal to 1. And you have equal sized reactors. So it is suggested that you will use equal sized reactors when N is equal to 1. When N is greater than 1, the optimum placement of reactors should be this: smaller reactor should come first, meaning smaller reactor then big reactor. So you cannot have a big reactor then a smaller reactor, because that scenario is suggested when the order of the reaction is less than 1. So take note of this. This even came out of the quiz bowl, in the national quiz bowl questions during peachy conventions. So this was asked, what is the optimum size ratio for uh, equal size reactors in series if the order of the reaction is greater than 1. So if it's greater than 1, the previous reactor should be smaller than the succeeding reactor. Otherwise, if it's less than 1, we should have a placement which is larger reactor followed by a smaller reactor. We don't have any problem if the order is equal to 1. Now, if we have equal size CSTRs in series for n MFRs, and for the order of the reaction equal to 2, still constant density, because we don't have here expansion or the, shall we say, the epsilon, the fractional conversion from 0% conversion to 100% conversion divided by volume at 0% conversion. This would be our formula. So actually, this one will have an n. This is dependent on the n, on how many radical expressions you should have is dependent on the n. So your C sub n is equal to 1 over 4k tau I, which is the space-time for your particular reactor times this. So it's actually a pattern. Negative 2 plus 2 square root of negative 1 plus 2 square root of negative 1 plus 2 square root. This is the last square root expression. On how many of this you will have. So you have negative 2 plus 2. It's now negative 1 plus 2 always. Square root of negative 1 plus 2 always. It will only end with this when you have it reached already n minus 1. For you to understand it better, I'd like to show to you the source of this particular formula. Let me have a new share, and we go to um, Levenspiel. Let me see. Okay, it's here. It's in chapter 6, I guess. Let's just... the case, chapter 6 is about recycle reactors, and it's before that. Okay, so here we go. Multiple mixed flow reactors of different sizes, and reactors with different sizes in series. Okay, it's the recycle reactor already. Let me check. It's maybe here. Second order reactor, second order reaction. Okay, so this is what we have discussed already. Second order, here it is, class. Okay, here it is. The number of radical signs that you should have here should be n. So if you will not account for this one, this number should be n minus 1. So let's say, for example, your number of MFRs in series is 5. So you should have 4 of this square root. This is already the fifth. The 1 plus 4 COK tau I. So I cannot write that in the formula, because if I use the equation editor, it could not, we cannot have this written. So you should, as I have said a while ago, this should be n minus 1, excluding this one. So it should be -2 plus 2 square root of -1 plus 2 square root of -1 plus 2. You will only end when you have reached the number n. So you should have n minus 1 rather. So you should have, if I said already, you have 5 MFRs in series. So you have -2 plus 2 square root of -1 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 plus 2 square root of this 1 plus 4 COK tau I. So this should be your fifth square root in your expression, because you have this as n. Okay, and that would give you the concentration on the nth reactor in your series of equal sized MFRs. So if I will go back to our slide, that one, that the thing that was not written, here is the n from here to here. But if it's just here to here, not including this one, that should be n minus 1. Now, this is how we use the graphical approach in determining the corresponding volume of a plug flow reactor, because you have a ratio here of initial concentration squared volume divided by molar feed rate for n reactors, referring to your mixed flow reactors. And you have here same expression, but this is for your plug flow reactor. That would be these two expressions here being equal to tau CAO for your n number of MFRs, to tau CAO for just one PFR, equivalent to this n number of PFRs. Now in here, although this is not often given much importance, because we'd rather solve than use a graph in getting our answer, because of course the answers will be dependent on how well you read the values from the graph. This refers to the number of MFRs in your series. And before you could even use this one, you need to solve for the value of the KCAO tau for your particular reaction. You solve for the KCAO tau and you determine the corresponding number of MFRs here. The intersection of the two will give you the, let's say for example, for a certain degree of conversion, for let's say 2 MFRs in series and a corresponding value for a KCAO tau in here, you'll be able to find the ratio here, the value of the ratio here, which will give you the volume of the equivalent plug flow reactor. If we increase the number of MFRs in the series, that would be equivalent to one plug flow reactor, provided that the volume of this plug flow reactor is equivalent to the total volume of your n number of MFRs in the series. Now, this one is specifically only to be used for second order reaction because we have a different graph to use if it's a first order reaction. I think you have also the same graph in your Perry's handbook. But nonetheless, I would still suggest that you use the analytical approach whenever possible rather than relying on the graphical approach. Anyway, in the sample problems that I will be using in a little while, discussing in a little while, you would all be using the analytical approach, meaning we go back to the formulas that were suggested in our general reference book, which is Leven's-Spear. So let me start off with this particular problem of a two-stage battery which is being used to obtain 80% conversion of the feed. So these are the given information. You have this as the volumetric flow rate, the initial concentration, and the rate law for your given reaction. After several days of operation, the flow is stopped. So meaning the connection to your two MFRs is cut. The two reactors are dumped when the average of their concentrations is the same as the steady state effluent from the last reactor under normal operating conditions. What does this mean? The original setup is that you will have a two-stage battery and it should have 80% conversion. Now, after several days of operation, this is the real scenario. You have a two MFRs arranged in series and it was not specified in the problem how long was this, but after several days, the flow is stopped and the connection between the two reactors is cut, or shall we say the two reactors now are going to process the feed inside them individually. So the two reactors will be dumped, meaning the concentrations of the mixture process in each of these reactors will only be dumped, or the operation will only be dumped when the concentrations individually on these two reactors are said to be, when average, equal to the concentration at normal conditions. So how do I say it? Normal condition, you have the operation of the two reactors. After several days, the operation was cut, meaning the connection to the two reactors was cut, but it doesn't mean that the reaction stopped inside the reactors. The reaction inside the reactor still proceeded. Now, when will be this particular scenario stop? So when the connection in the two reactors was already cut, the operation of the two, meaning the succeeding processing of the converted material inside the reactor, will only be stopped when the average concentration between these two disconnected MFRs will be equivalent to the concentration when it was not cut. So actually, when I discuss this particular problem, I have difficulty in really making it clear so that the student would really understand the subsequent calculations that will be done. The problem is how soon after flow is stopped can the material be discharged. So meaning, uh, after the connection between the two reactors was cut, and the reaction was allowed to proceed in the two reactors, wherein the reactors are to process the thing inside their units individually, how long will the processing would be in such a way that when you get the average of the concentration of the two MFRs processing the content separately will be equal to the concentration of the effluent of the last reactor when the operation is as expected, meaning you don't cut the connection between the two reactors. So how soon after flow is stopped can the material be discharged? So instantaneous discharge is to be assumed. Okay? Okay, let me start with, okay, let me show to you how is this particular problem be tackled. So let's go back to our board and try to write down the given, the required, and we'll find a way to determine what the problem requires. So this is our first sample problem. So this is case 1, the original scenario. You have two MFRs in your system, and your initial concentration here is 1.5 pound mole per cubic feet. The rate law is given as 0.2 Ca with set of units pound mole per cubic feet per minute. This is Ca2 based on our labeling. This is Ca1. This is Xa1. This is Xa2. And we have here FAO, XAO. Okay. Conversion in this particular scenario is expected to be 0.8. I did not write any number here, so meaning it's referring to the entire system. The degree on conversion expected is 0.8. So you are required to find T when, let's say for example, in this scenario, when after several days, with this being Ca1 because it already reached a certain degree of conversion because the original scenario was this. You will have a certain concentration here, let's say Ca prime. And in here, you already have, by the way, originally, I'll just place here some sort of a line, meaning there was a cut already. And by the way, in the first one, there was no cut because it's not connected to anything. So we'll get, sorry. So in your first reactor, you only have this. Nothing is entering anymore because this was already cut. T, when after several days, connection was cut. So in here, I'll just place this sign, meaning the connection between the two was cut. So we are after, so this is Ca2. At the time the connection was cut, so you will have a corresponding concentration here of Ca, let's say double prime. I hope you understand this, okay? Originally, this is your scenario. After several days of operation, I like to use a red line. This was cut. And of course, we expect that the thing inside the reactor was already partially converted, and that is Ca1. And if this particular reactor will continuously process the partially converted uh, mixture inside it, then the corresponding discharge from it will be having a concentration of Ca prime. This one is just a copy of this because this one was cut, but there was no anymore, there was no continuous movement of material to reactor 2. And you have the concentration here of the pre-processed feed inside reactor 2, and that's already Ca2 because this is after several days, so it's not the original concentration anymore but the converted concentration. The reactor will process this standalone. This one will also process the thing inside it standalone. This one will have a converted concentration of Ca prime. This one will have a converted concentration of Ca double prime. So this T, when after several days connection was cut, you are to find the T. So this is a question mark actually. T when. So for you to know how you're going to find the required information, when Ca prime plus Ca double prime divided by 2, because we're talking about the average, is equal to the Ca2. And what is that Ca2? This is the Ca2 when we have the scenario fitting the original problem, meaning uh, the connection is not cut. Okay, I will read the problem again. That way you will fully understand the representation that we have here. So I'll go back to the slide. Where is the slide? Okay, a two-stage battery is being used to obtain 80% conversion under the following conditions. So these are the conditions, the given information. After several days of operation, flow is stopped, meaning the connection cut. There was no flow in the first reactor. The two reactors are dumped when the average of their concentrations is the same as the steady state effluent from the last reactor under normal operating conditions. So meaning when the flow is stopped, it doesn't mean that the content of the reactors were discharged, but the reactors will still process the partially converted material inside them. They will process it for a certain degree of amount of time. When will be the processing stop? So this is the question that the problem asks you to answer. How soon after flow is stopped can the material be discharged, with the scenario that the average concentration should be the same as the steady state effluent from the last reactor under normal operating conditions. The normal operating conditions that is being referred to is here is when the flow will not be stopped, meaning it would really function as a system of two MFRs in series. Okay, so now let's go back to our solution. So the first thing that we will do in this case is, of course, determine the concentration. What is the concentration at normal condition? So Ca2. So it says there that there should be 80% conversion for the entire system. So if it's 80% conversion, you will have CaO times 1 minus Xa. Your initial feed should be converted in such a way that the final concentration leaving the last reactor will be 80% converted. So in that case, you will have 1.5 here, 1 minus 0.80. Okay, so CaO1 minus Xa, and this is the expected final concentration in the last reactor. Okay, that way we will have a 80% conversion. So your final concentration would be 0.3 pound mole per cubic feet. So this is the Ca2 that we will equate here later. So the Ca2 asterisk that we will equate later to the Ca prime plus Ca2 double prime divided by 2. So now that we have that, a while ago I've showed you an equation which is giving you the Co over the Cn equal to 1 plus k tau raised to n. This formula for an equal size MFRs in series allows you to determine whichever of these two concentration is unknown. Okay, now you will need in this case this particular equation. That way we can find the space-time for each of our equal sized MFRs. In our case, our initial concentration in this problem is 1.5. We need to divide that by this concentration that we just determined. And this will allow us to determine the tau. Our K is given by the rate law, so I will not go back to that anymore. We just we wrote it on the given K tau, and our N is equal to 2. So in this case, you'll have a value for tau, which is tau 1, tau 2. So the same tau for each of our equal size MFRs. The value is 6.18 minutes. Okay? And that's our value. Now, since we already have the space-time for our reactors that are said to be equal size, going back to the same formula, we can now determine the concentration for the first reactor because we know already that this is the concentration leaving the last reactor. We need to know the concentration leaving the first reactor. So using the same formula, this time I'll write CO over CA1 is equal to 1 plus K tau. Of course, this has to be 1 because my concentration here is 1. Here, it's 2. Your CAN, your C sub n here rather, is Ca2 because the n that I used is 2. Okay, so if this is 3, then this must be Ca3. So since I'm now looking for Ca1, so this must be 1. So same thing, you will have 1.5. I want to know Ca1. I will have 1 plus k tau raised to 1. This is 1 plus 0.2 times the space-time that we already know to be 6.18. Okay, so that's our right side. This will give us a Ca1 value equal to 0.6708 pound mole per cubic feet. Now, take note that we'll be using Ca2 and Ca1. We'll be using these two concentration when we make a setup or another set of equation in which each of our reactors will function already separately. After several days of operation, they will function separately, and the initial concentration that they will process would be this partially converted concentration here. They will process this particular concentration and have their final concentration of effluent, of course, different than these two. Okay, now I will have another sheet here. Then for n equal to 1, since our rate law is 0.2 Ca, so our n is equal to 1, we know that C is equal to CaO, let's say for example Ca1 or Ca e raised to negative kT. So we know this already for a first order reaction coming from this particular expression, negative dCa dt is equal to kCa. So if we will process this differential equation, we will have this. Final concentration is equal to the initial concentration times e raised to negative kT. Now, if we go back to this, values that we have here, this will be the initial concentrations in our two reactors. So this is the initial concentration for the first reactor, and this would be the initial concentration for our second reactor, because of the fact that the connection was already cut between the two. So in that case, this would be in the case of the first reactor. So for N, shall I say N1, when the operation was cut, your C prime would be Ca1 e raised to negative kT. Okay, it has to start from this partially converted concentration. So that would be your Ca1, which we got in the previous slide, is 0.6708. So this would be 0.6708 e raised to negative 0.2 t. Our C double prime will have to start with an initial concentration of 0.3. This one, because this is our concentration leaving the last reactor for this particular degree of conversion. So it will have to start with that concentration. So I will place here Ca2 e raised to negative kT still, and this would be 0.3 e raised to negative 0.2 t. Now, if you recall, we have written in the required information this particular scenario. So I'll place here your C prime plus C double prime divided by 2 should be equal to Ca2. So these two formulas here have the time. So that's the time that we are asking. When will these two separately, when will be the two reactors separately processing the partially converted mixture inside them stop operating? When the average of their concentration is equal to 0.3. So we have here 0.6708 plus you have 0.3. I will just multiply them to e raised to negative 0.2 t, because anyway it's the same for the two. We divide by 2 and we equate that with 0.3. 0.3 is the expected concentration when the connection between the two reactors was not disconnected. So in here, we can have the time computed, and the value of this time is 2.4 minutes. This is the time after the connection between the two reactors was cut, where we need to also stop operating the two, because the concentrations inside The two reactors will now be in these two expression. And if you're going to get the average, that would be equal to 0.3, which is the expected concentration. When the first case, the normal case in which the two equal size reactors are processing the same feed continuously, meaning there was no stop in operation and there was no disconnection between the two reactors. So hopefully I made things clear, but if it's not that clear, you can always message me or drop me a line in Canvas for this particular set of slides if you don't have uh, a clear understanding of this particular sample problem. Okay, so now let's go to our next discussion. And we're here already. Let me check. Okay, so we have now this scenario wherein we have MFRs of different sizes. The representation is pretty much the same, but this time, of course, they are not equally sized. So they are different in sizes. So your space-time would still be actually based on the original formula for the performance equation of an MFR. The tau is equal to the part that has been converted, the CO minus C1 over the rate expression. What I like so much about MFRs is we don't need to integrate. Or we can have an alternative expression like this. It's just actually the inverse of this, then the negative reciprocal rather of this original expression. So you have this particular formula for this one to use. Okay, we go back to the fundamental basic principle of the performance equation of an MFR. And this particular scenario will be applicable also to this uniquely sized MFRs in series. So if it's referring to tau for the space-time of the second MFR, this should be tau 2, this should be V2, this should be V. This should be, by the way, the same for all your MFRs. And in that case, this would be C1 minus C2 because this is already tau 2, and so on and so forth. Now, there's a question here. Can we model PFR as a series of n equals CSTRs? So of course, if you were attentive in the discussion a while ago, this can be done as long as your CSTRs are of equal volume. So you can model it as one PFR of volume equal to the sum of the volumes of your CSTR. Okay, now compare volume of the following two cases. You have a single reactor achieving X3, meaning a single reactor, MFR reactor achieving a certain degree of conversion X3 in this scenario, or three reactors in series achieving X3. So you have this. One scenario is just one reactor achieving X3, and another scenario is three reactors achieving X3 here, the degree of conversion in the last reactor. How is the total volume of the three reactors in series, this one, if you're going to add their volumes, related to a single MFR? Now, I leave that question to you to check. You can start with just two MFRs in series. What do you think would be the volume of the two MFRs in series which are not equal in size in comparison to the volume of just one single reactor? Now, in this case, the tying factor that you will use is that the scenario in which you have two MFRs, for example, in series, and you just have one MFR, which of the two will have a smaller volume? Will it be the two MFRs in series or the one MFR in series? So that's the big question here, because this one we already know to be possible. So this one you will learn if you will really practice solving problems in Levenspiel regarding MFRs which are not equal in size and arranged in series. Now, what about, so we know already how to process PFRs in series. What would be the connecting principle or variable that we can relate PFRs that are arranged in parallel? We have already discussed MFRs in series, equal size and unequal size. What about if you have different reactors already? So you have CSTR, PFR, and then another CSTR. How do you determine the X sub n, or how will you represent X sub n? So this would be the moles of A reacted up to reactor N over moles of A fed to the first reactor. So the number of moles of A originally processed by your first reactor now being compared to the number of moles of A reacted up to the reactor N. So this particular expression is valid with no side stream. So meaning there are no removals here, meaning all streams from one reactor is being processed by the succeeding reactor. The same thing with no added streams here. Let's say, for example, in the PFR, other than the one coming from the first reactor, which is the CSTR. This particular formula you can also see in Levenspiel. So this formula is for your CSTR, for your first reactor, no integral. This will be your formula for the PFR in the second reactor. Now this time you have the integral because you have a PFR, and this one is for your third reactor, another CSTR. You will still need to go back to the basics of the performance equations of each of these particular reactors. So performance equation for an MFR here, the same thing in here, and this one is the performance equation for your PFR or your tubular reactor. Now, if it is to be interpreted in terms of the area of the graph, just like in your integral calculus, if you have this one, this represents the area of the curve on the designated interval or boundary, referring to the limits of your integral. The two MFRs will have areas representing rectangles because we don't integrate. The blue one here in the middle is for the area under the expression for the volume of the PFR. So this would be the three areas that we will be computing if we want the volumes of each of these three reactors. So this is the volume for the first CSTR. These two can be your, any of these two can be your formula for the volume of the plug flow reactor, the second reactor in the series. Anyway, this one just came from this one. And this one is your performance equation for the third MFR. And that brings about this particular reaction for us to solve. So an elementary irreversible aqueous phase reaction A plus B forming R plus S is carried out isothermally as follows. Equal volumetric flow rates of two liquid streams are introduced into 1 cubic feet mixing tank. One stream contains 0.02 mole of A per liter, and the other is 1.4 mole of B per liter. The mixed stream is then passed through a 4 cubic feet PFR. We found out that some R were formed in the mixing tank and the concentration of which is 0.002 mole per liter, which makes the mixing tank function like a back-mix reactor. Now, what is the concentration of R at the exit of the PFR and the conversion of A in the system? So this is already a case in which you have a combination of reactors, a CSTR and a PFR. So I'd like us to go back to our board and write down the given information. So this is our second sample problem. For our second sample problem, we have a CSTR followed by a PFR. So we have a feed here, the effluent here being introduced to your PFR. And you have this one. So this is CaO. By the way, we have two streams being fed to our first reactor, so we cannot just have a CaO. So in this case, I'd like to move this up. I have to have it like that. Okay. So one stream is containing B, 1.4 mole B per liter. Another stream has A, 0.02 mole A per liter. Now, this will have, let's say for example, this will have a volumetric flow rate of VB. This will have a volumetric flow rate of VA. The volume of the mixed flow reactor is 1 cubic feet. Now, it was observed that there's a partial, let's say, formation of R in the tank, in the mixing tank. That is why they have concluded that the tank is not a pure mixing tank, but an MFR or a CSTR. So 0.002 mole R per liter. So this is the content of R in the effluent coming from the first tank. So we will have, of course, as expected, we will also have CA1 and CB1 here because we have A and B originally. And for your PFR, the volume is 4 cubic feet. And you are asked to find here the concentration of R leaving the PFR. And aside from that, if this is the given, you're required to determine also the degree of conversion of A in the entire system. Okay. Another thing that we can write here, it was stated in the problem that the flow rate of the two streams are equal, the streams being processed by the CSTR, the first reactor. And if they are equal, we can write this as VA plus VB being equal to V, okay, for our first reactor. Our reactor is liquid phase, so then this is the fractional conversion or the expansion factor. And this is our equation, stoichiometric equation, A and B reacting to form R and S. Our rate law, then, in this case, since this is mentioned to be an elementary reaction, homogeneous liquid phase reaction, we can write the rate law to be KCACB, okay, based on the reacting species. Now we will start with our solution. I think this is similar to one problem that we have discussed, but the thing is that problem is only talking about the CSTR. It was not combined with another reactor. So in this case, we will recall what we did to determine the actual concentration of A and B if these two streams are already mixed and allowed to react in the mixing tank. So in that case, if these two are equal, so let's say this is 1 unit and this is 1 unit, so we can say that your CaO, your initial concentration for CaO will be 0.02 divided by 2. So that would be 0.01 mole A per liter. Your CBO would be then 1.4 also divided by 2. So we have 0.7 mole B per liter. So looking at the two concentrations, we know that the limiting component is this one, A, limiting reactant. That's your A. So we will base our performance equation on the limiting component, which is A. Okay, so we will go now to, we'll have another sheet, and we will write the performance equation for the mixed flow reactor. I hope you fully memorize it by now. And that would be equal to the rate law. So I will have here CaO, we know already to be 0.01, and I have here XAM. The rate law will be written as K. You have CaO 1 minus XAM, because we're talking about the conversion here in the mixed flow reactor, times CBO minus CBO XBM. Okay, now this is equal to actually volume over volumetric flow rate, volume of the mixed flow reactor. So we can have 1 over V is equal to CaO 0.01 XAM. You will have, and by the way, we already have CaO on top, so we can cancel this CaO and this CaO. So we can do that, but we will not have to write it again. So we will cancel this one. This is actually CaO. I'll cancel and cancel. So I will have, I don't need to write it here anymore. Okay, so you have XAM, and you will have K. Oh, anyway, you have K 1 minus XAM. Your CBO is, by the way, 0.7, right? 0.7. And your CBO XBM in terms of stoichiometry will be 1:1. So the CBO XBM in terms of stoichiometry, all right, CBO XBM is equal to CaO XAM. Why? Because the equation that we have is just like this. This one, okay? So we have this. So this would be now 0.4, and I will have to write here CaO, which is 0.01 XAM. Okay? So this will be our first equation. Now, our CR prime is actually our CRO1 plus XRM. That's in the mixed flow reactor. And since we don't have initially R, then this would be CRO XRM only, which is also equal to CaO XAM, CBO XBM. I can write this to be equal to, since it was mentioned already that the amount of R form is 0.002. So I'd like to write that as 0.002. Now, XAM. Okay, so you will use now KB. So we will have from equation 1, we can get the expression K, transfer the K here, over V being equal to XAM over 1 minus XAM, 0.07 minus 0.01 XAM. Okay, that's from our equation 1. I can solve for the ratio of K to V, which are all constants, by the way. This is a constant, that one is a constant, by getting the value of XAM in here. So 0.002 is equal to CAO XAM. 0.002 is equal to our CAO. What's the value of our CAO? 0.01. 0.01 XAM. So we will be getting the value of XAM in here. So it's not able to compute it. So our answer is 0.2. And with that, we can go back to the equation that we left here. Let's say this is equation 2. So I'll just write here, substitute XAM equal to 0.222. Okay, that should give you a K over V ratio of 0.3582. So we'll have this as our equation. Actually, it's an expression, but nonetheless, we will represent it as 3. Now, let's go to our plug flow reactor. For the plug flow reactor, we have its volume divided by the volumetric flow rate, and that would be CAO, integral of dxa over the rate. But this could be changed to in terms of conversion, in terms of concentration. CAO dxa is actually negative dca over the rate. So you will have here in the plug flow reactor CA1 to CA2 as your limit of your integral. Your plug flow reactor is 4 cubic feet. So we divide it by V. And I would like to use this one. You have negative CA1, CA2. So you have DCA. And I'd like to write the rate law here. K CACB. Now I can transfer the K here. That would be 4K over V is equal to negative of the integral from CA1 to CA2 of DCA over CACB. Okay, the K I already transferred on the other side. The purpose is for me to be able to use 3 here for the K over V. So I will have 4 times 0.3582 is equal to, excuse me, you have this negative DCA negative integral of DCA CA1 to oh Never mind that. So you have Ca2, you have Ca, and then we have Cb to be Cbo minus Cbo Xb. Now, our purpose of writing it in this manner is that we can replace this expression in terms of Ca because our differential is in terms of Ca. So I'll have here negative integral from Ca1 to Ca2. And you have dCa, sorry, Ca. Our CBO is zero point 0.7. Our CBOXB is CAOXA. Now, how can we change the CAOXA in terms of Ca? There's a need for us to convert the CAOXA into an expression which could be expressed in terms of Ca. So we know in the fundamentals of kinetics that this is the portion reacted. So the final concentration is equal to the initial concentration minus the portion reacted. So I have now an expression to change this one. So CaOXA is equal to CaO minus Ca. So I'll go back here. This would be negative, again, Ca1 to Ca2 dCa divided by, so you have a Ca, and I have a 0.7 here, and this CaO is this. So that would be negative, your CaO is 0.01, negative, and this is negative, so that would be positive. So plus Ca. So hopefully you can follow through. This 0.01 plus Ca is this. CaO is 0.01, negative, negative, so that would be positive. So your integral now, yet what you'll be having on the left side, if you will transfer the negative sign in here and process the product of these two, will be negative 1.4328. Okay, integral from Ca1 to Ca2. dCa over, so this 0.7 minus 0.01 is 0.69. So you have Ca times 0.69 plus Ca. Okay, that's more like it. So this is now our integral. Now, how do we process this expression from integral calculus is through the use of the method of partial fractions. It would not have been difficult if we know already the limits, but in this case, it's one of the limits that we are after, and that is the Ca2. We need to know the Ca2, that way we can determine the degree of conversion for the entire system of A. So we'll have another slide here. So you will have to do method of partial fractions. I will not show the entire process here. Let me see. So you have 0.69, and you have here. So you need to know the two coefficients here. Okay, so just two. So you have A, that would be 0.69 minus Ca plus B, and then you have Ca. Now, if we will this is it, okay, and this is 1. So if we will equate constants you have 1 is equal to 0.69A. Your A will be equal to 1.45. If we will equate, so this is for constants. If we will equate CA, so you will have 0 is equal to negative A plus B. Then B is also 1.45. Then our integral, so we will just copy the negative 1.4328, and you will have two integrals having the same coefficients. So dCA over CA plus 1.45 dCA over 0.69 plus CA. Now, since we have 1.45 and 1.45 here, we can transfer it in here. That should give us negative 0.9886. And if we will process this integral, same thing here, this will be equal to the ln of CA2 over CA1. The other one will be the ln of 0.69 plus CA2 over 0.69 plus CA1. Okay. If we will combine these two ln's, wait, is it positive or negative? B is positive. Okay, so if it's positive, then this should be ln of, so this should be multiplied CA2 over CA1 times 0.69 plus CA2 over 0.69 plus CA1. Let me see. This is negative 0.9886. This is negative 0.9886. And CA1. Okay, so I have ln of CA2 times 0.69 plus CA2. CA2, our CA1, we need to know. So we need to know CA1. Sorry. CR prime in the backmix reactor or in the MFR also refers to CA. The CA prime is also equal to CaOxAm. This is 0.002. That's your CaOxAm. Now your CA1 will be your CaO minus your CaOxAm. So then your CA1 will be your CaO, which is 0.01. Let me check if it's also 0.01 already. Yes. And with XAM minus 0.002 XAM. So that should give you CA1 being equal to 0.008. That's the CA1 that you will place here. 0.008 times 0.69 plus 0.008. Okay. Now, for us to be able to get rid of the ln, we need to raise the entire equation or make the entire equation be the exponent of the e. And that would be, let me see. Excuse me, class. I'll just get my calculator. Okay, if this is raised or make the exponent of the e, we will have it equal to 0.3721. And our expression here, we will copy without the ln. So we have Ca2 0.69 plus Ca2. We divide by 0.008. Point 0.69 plus 0.008. So we will just process it as 0.008 times 0.69. Oh, 0.008 plus 0.69. So 0.698. So if you process all of this, that would be 0.002078. And that would be Ca2 times 0.69 plus Ca2. So this is a quadratic equation. You will have here 0.69 Ca2 plus Ca2 squared. And you have here 0.00278. So your Ca2 can be, if all of this is in here, negative 0.69 plus minus the square root of 0.69 squared minus 4 times 1 times negative 0.002078 all over 2a if you use quadratic equation. So you have negative 0.69 plus minus. So you have times 4 plus 0.69, you square it. Then you get the square root of the answer. So that would be 0.6959 divided by 2 times 1. By the way, our A is 1. So since we cannot have a negative concentration, we'll consider this being added to this. So you have 0.69599 minus 0.69 divided by 2. So your Ca2 is 0.002998. That's our Ca2. Okay. If we know the Ca2, then we can find the Xa. So we have our degree of conversion is equal to initial concentration minus final concentration over the initial concentration, because this is referring to the degree converted if I do cross multiplication. So your CaO is 0.01 minus 0.002998 divided by 0.01, giving us an Xa equal to 70. So our degree of conversion is 70. So that's just one of the requirement, because we still need to find the C sub R leaving the PFR. Okay, let's have another sheet. In the PFR, if you do material balance, the degree of R formed is equal to the amount of A. So that would be CA1 XA2, the amount converted in the PFR. The amount converted in the PFR, which is CA1 XA2, is actually CA1 minus CA2. Now, since we know already CA2 and CA1, we will know this one. So CA1 is 0.01, CA2 is 0.00. I'd like to cut this short to 0.003. Round it off. So you have CROXR value of 0.007123, 0.007. So that tells us that the C sub R leaving the PFR is the C sub R that was formed in the PFR plus the C sub R formed in the backmix reactor, which we'll label to be C sub R prime. So our 0.007 should be added to 0.002. So the concentration of R 0.001 weight class. I made a mistake, I think, in here. For the PFR, that would be CA1. Our CA1, I placed here CAO. Sorry. So we'll change this. Our CA1, did we compute already for CA1? Let's go back. 0.008. So this is our CA1. Sorry, I substituted the CAO. So you have 0.008. So this should be this is 0.005. 0.005. Your C sub R is 0.007. What's our set of units here? That's mole per liter. Oh, by the way, wait. Our volume is in cubic feet. And our concentration is in liters. So I computed here using the, so there's no unit here, weight class. Cubic feet. My volume should be in liters because my concentrations are in liters. So as not, we will not redo everything. let's assume that the problem is giving you a volume in liters. So I will edit the slide with the volume or in cubic feet to volume in liter. That way, there's no need for us to do the conversion. Anyway, what is important is the principle that was illustrated in determining the required information. So good that I was able to see it. So that we will have everything in the unit for volume to be in liter, we will just consider that the given information in the problem concerning the volumes of our reactors are in liters. So I will just change this one to liters. Okay. And we'll also have the problem edited in a little while. So this is 1 liter. This is 4 liters. That way we will not edit anymore. Okay, so this is how we solve the problem. It's quite lengthy because of the mathematical procedure that we need to do. Okay, but the thing is we only went back to the performance equations of the individual reactors and have them connected. Okay, let me see. So let's go back to our slide. So this is where we are. Okay, now this is our third sample problem. The solution of this will be quite lengthy. I will continue discussing this problem uh, as part 2 for this particular set of slide, because as of now we're more than already an hour and it would be lengthy for you to process everything in one setting. So I will have a different recording for this third sample problem and finish the entire slide of multiple reactors. So till next time, class. Thank you for listening.